Okay, I would like to discuss PID Control. This is the beginning of several lectures regarding the topic because it is an algorithm that is used extensively in the industry, and it's important for us here in mechatronics. PID stands for proportional, integral, and derivative control. Okay, these are mathematical operations done on a signal, in this case the error signal, and we'll see eventually on the feedback signal that we are reading. I would like to maybe explain this with an example here. We have a ball and beam device. The goal of this is to maintain the ball right in the center of the beam, and in order to do so there's a DC motor that has the beam attached to its shaft. Okay, we have a sensor in one end, proximity sensor of any kind, and depending on the position of this ball, the actuator, the DC motor, should counter the error discrepancy between this set point distance, which is R here in orange, and the desired, rather the feedback signal Y. Okay, so the idea is that Y follows R. Wherever R is, that's where we want the ball to be, and Y should go accordingly. So to maybe start explaining proportional controller, I have two scenarios, A and B, of this ball. We could apply some sort of disturbance in one end of the beam, either up or down, and in doing so we have these two cases, A and B. So let me show you what that means. In case A, we have, actually let me zoom out a little here. So we have a couple of scenarios. Case A shows when we are pushing that beam from the left upwards, okay? And case B is when we're pushing it downwards. So obviously if we push this up, the ball displaces to the right, and the sensor is perhaps reading 3 centimeters now. Whereas in case B, it's now 7 centimeters. It's moving away from the center. Now the key to proportional control is to define the error signal. Now the error signal will always be defined as the difference between where you want the ball to be, that reference, and where the ball actually is. That's the feedback signal. And so if we define this error between desired and actual positions, we can somehow figure out a way to supply a voltage to the motor which is proportional to that error. Okay, so if there is an error signal, there's a voltage being sent to the motor. If there's not, nothing happens. And this constant of proportionality is known as the P gain, the P controller. Now for this example, I'm just randomly choosing a value here of 3 volts per centimeter. That means that for every centimeter that we register in the error, there are going to be 3 volts applied to the motor. Okay? Now if that's the case, let's see what happens in scenario A. In scenario A, if we place the motor leads in such a way that that polarity plus a supply voltage causes a counterclockwise direction, this is the response in terms of the magnitude of the signal. We defined the supplied voltage to the motor as this P gain times the error. The error in this case A is 5 centimeters minus 3, and that is positive 2 centimeters. So taking that gain, which is a constant, and multiplying by the error signal, which changes, for case A gives 6 volts. So 6 volts are applied to the motor counterclockwise, and that will spin counterclockwise. Essentially what that does, it wants to bring the ball back. Okay, it's rolling downhill towards the right. By going counterclockwise, I bring it back to the center. Now with the same equation, the opposite is true on case B. In this case, I'm putting a disturbance here. The ball rolls to the left, and the same equation now gives a negative error of minus 2 centimeters. Again, with a constant of 3 volts per centimeter, we have a final supply voltage to the motor of minus 6 volts. And in this case, automatically the polarity changes. We don't have to be changing this, the signal changes. So in our logic, when we are coding this, we just account for that change in sign of that magnitude voltage. And this is essentially what proportional control is. If the polarity changes, well, for a DC motor, it simply means now we're spinning clockwise direction, and it wants to bring the ball back to the center. And that's essentially what proportional control is. It's just a way that we use the error signal to supply a voltage to the actuator, and it automatically makes the correction in the opposite direction of motion of, in this case, of that ball. Okay. Now the question then is, what is the value of the gain that we must have in order to meet some customer specification? So for example, if I pay the engineer $1 million to design such a device, my specification would be, please make sure that the ball, when it is displaced, it goes back within a certain amount of time, within 1 second. And not only that, but when it comes back within a second, make sure it doesn't go back oscillating. It overshoots and then comes back and undershoots and keeps oscillating. That is not allowed. If it has to oscillate, make sure that it does so within a certain amount of time, within half a second. That's called the settling time. And all these time parameters, that is something that we factor into this gain. Okay, and classical control theory talks about ways in which to graphically obtain that gain with this thing called root locus, or we can also use what's known as block algebra and transfer functions to analytically obtain an expression, an equation for this KP number, that gain, in terms of time domain specifications from the customer, and also the behavior of the system itself, which is called a model. And this is where we need to know how the ball actually moves, and we have to come with equations of motion for that ball, okay, based on angles, based on gravity, and that equation should give us this thing called a transfer function, which is really a ratio of an output signal to an input signal. And that the entire controls class is devoted to transfer functions and how to come up with these gains, that when we close the loop, closing the loop means that the signal of the actuator is completely dependent on what the sensor is reading the system doing, that closed loop control is able to behave in a way that we want to. Okay, and this is proportional control. So I speak a little bit about this written here, but now we want to go a step further. Proportional control is really static control. It has nothing to do with time, right? It's immediate. So if there's an error, there's a voltage, period. Okay, instantaneously it happens. There's no delay. There's no S domain in the transfer functions for those who are familiar with that. No integration, no anything. This is simply the most basic controller. There's an error, there's a voltage, period. Okay, based on that constant of proportionality. Now, if we, let's say, if we apply this proportional controller to this system, we would very quickly realize that the ball will never settle in the center. Okay, what actually happens is this ball starts oscillating back and forth, It wants to get there, but it can't. There's something happening, and this is where control theory comes in. Why is it not settling down? What's the problem there? And the problem has to do with specifically time. We have not factored any time considerations in here for our design. And this is where the proportional controller needs a little help from some other mathematical operations. In this case, we're going to be talking about integration and derivation and see what happens when you integrate, okay? And that's next. So this is proportional. Now, let's talk about integration and what it does, okay? So let's look at this for a second. I'm going to pull back, and I'm going to show these two plots, okay? The first plot is a plot of the ball's position. So that is the blue line that we see. And the bottom plot is the voltage that is being sent to the DC motor, okay? Now, I have divided this response in two regions. Anything from T2 to the left is only proportional control, and from T2 to the right is proportional plus integral control. So let's see what happens from the left, okay? So from the left, anytime from 0 to T sub 0, the ball is right at the center at 5 centimeters, okay? That's what we kind of stated here. That's our desired position. So we're at the center, therefore there's no voltage happening to the motor. Everything is fine. All of a sudden at T0, there is a disturbance, so somebody's pushing that ball so that it moves closer to the sensor at 3 centimeters. Now, because proportional control is proportional to the error, we have the error signal denoted by these red arrows, okay? So the error is the difference between 5 and 3, and at time T sub 0, it is 2 centimeters. Immediately, there's a voltage that occurs, whose magnitude is the gain Kp, which arbitrarily we chose as 3 volts per centimeter, times the magnitude of the error, which is 2. So 3 times 2 would be 6. So at T0, boom, immediately you jump at 6 volts. Now, jumping, you're sending voltage to the motor. That would be equivalent to case A, right? So you're sending 6 volts in here, and it wants to completely rotate the beam counterclockwise. Now, as it is rotating counterclockwise, the ball is going closer to the set point, which is R. Okay? So that's what we see in the upper screen here. We see that the ball is getting closer to R, which is 5 centimeters, therefore reducing the error signal. As the error signal is reduced, the voltage to the motor is also reduced because it depends on the error. Now at some point that reduction is going to continue, but proportional control only gets you that far. You're still going to have some sort of what is known as steady state error, an error that lingers after a while, and that is denoted by, again, the red arrows. So at T sub 1, I just denoted E1. We follow the dashed lines, and that really means that the voltage at that moment in time is 3 volts per centimeter times E1, whatever E1 is. It's a very small number, okay? So we see that for every instance of time, this voltage is actually going down, but then it remains there. It doesn't do anything more than that, okay? This is where integration comes in. So imagine that at T2 sub 2, I have a switch, and it allows me to have integration. And by integration, we're adding now to the proportional term integration of the error multiplied by this other number called the integral gain. Okay? Now essentially it's taking the previous error, so that little red line, and amplifying it and adding it to whatever you had before. So this line, supposedly, right, you're adding this much in terms of voltage. That orange, these orange rectangles represent integration of a previous value of the error. Now, what that causes is it little bit increased the signal, rather the position of the ball getting closer and closer to my reference of 5 centimeters. So at each time step delta t, now keep in mind integration, it means delta t is very, very small. It tends to dt. So these rectangles are very thin, right? And close together. So these lines are creeping in as integration continues. Now, as the ball is getting closer to the set point, the error obviously goes down, which is what we want, which means the blue proportional controller goes down. And what remains in the end is entirely an integration signal. So V3 is at time T sub 3, and we see that the proportional controller, the blue signal, has vanished because there is no error at that point. The steady state error is 0. And this is essentially what we're doing by integrating, by adding up the error signal over time. We're closing the gap between R and Y and having the steady state be equal to 0. That's exactly what we want, okay? So integral control takes care of steady state criteria. Now there's a caution here, okay? I'm explaining this similarly to this setup in terms of ball and beam. However, the word of caution is that this is not really what happens with a ball and beam. This is the response that you would see for a first order system. The ball and beam is not a first order system. This is only for illustration, so you understand what's actually happening. This response is most likely for a DC motor by itself, spinning by itself. So when you put a voltage, you'll see that the motor ramps up in a first order fashion. You see an exponent, right? So it's ramping up and then it settles. So this is more like that type of response for closed loop control. Okay, it's just for illustration. All right, so that's what integration essentially does. Let's see if we can now take care of not only the steady state error, but things that are transient here at the beginning. Okay, and that's where derivative control comes in. By the way, before we leave integral, this is a MATLAB Simulink run of a closed loop control for a DC motor. So in this scenario, I divided the proportional control from 3 seconds and below. That is the closed loop response of the DC motor. Okay, the set point is 100 RPM, so I want my motor to go from 0 to 100. However, with proportional control, it only settles to 80 RPMs with this specific gain that I have. Okay, so as you increase that gain, this gap gets smaller. However, after 3 seconds, I apply integration, and the motor now slowly creeps to the 100 RPMs, eliminating the steady state error. Down below, you have both signals. Blue is proportional, orange is integral, separated. Okay, and you can see that integration goes up, right? A proportional goes down, and the last one is both combined, right? So when you add these two signals, you get that signal over there, all right? And that's essentially what's happening. This is for a first order system again. Let's talk about derivative control. So in this case, I want to show you what happens graphically. So let's go here first to plot 1. Now let's imagine for now, this is sort of more like it in terms of the response the ball would experience once it is controlled. Okay, so the y-axis here is normalized, which means I'm just taking the minimum and maximum bounds. 1 is my set point. That's where I want to go. Okay, so in this case, imagine 1 is 5 centimeters. Okay, and I'm somewhere else. So this is what the ball would do in a certain amount of time. Eventually, the blue line where the ball is would match the green line where is my set point. That's the center of the beam. Now, in this case, I have I jotted down or rather simulated this blue line as proportional control. That would be if I had proportional control, which I already explained. It's not really the case here, but let's assume it is. That is plot 1. Plot 2 is essentially capturing the error signal. So the error will always forever be the difference between reference, which is the green line, and the blue line at any given point in time. Okay, so if you put a vertical line and you say at time 0, you have 1 minus 0, and the answer is 1. So that's the error. At let's say time, whatever this is, like maybe 3 seconds, you have 1 minus, this looks like something close to 1.5, and that would be negative 0.5. So that's why we have negative values in here. So this plot is essentially the error signal. Okay. Now, if we, for argument's sake, say that the value of Kp is 1, then the proportional controller is the same as the error signal. So let's just assume that for now so that we can see this is not only the error, but it's also our pretend proportional control voltage being sent to the motor. Now notice that when the ball reaches the center here in the green line, there is no longer any need for any voltage to be sent to the motor, right? You are where you are, you don't want to rotate this anymore. And that's done right there. and the voltage always goes in the direction opposite of the motion of where the object is going, right? And that's so the controller compensates for that disturbance. So if this guy goes up, then the voltage is saying, oops, go counterclockwise in the opposite direction where that guy is going. Okay, let's go to plot 3 here. Now, let's imagine that someone is wanting to know what is the error rate of change, the rate of change of the error with respect to time. So essentially they're taking plot 2 and deriving it. So we're going to take that blue line and take the derivative. Now notice here that at the when the plot 3 is the slope, essentially the slope of plot 2. So in this instance, when the slope is right there, 0 slope, if you go down here, you see that you have 0 for your dE dt. Okay, that's 0 right there. Whereas if you have a high rate of change, a high slope, at this point, you have a high value of positive dE dt. Okay, because that's a positive slope and that's a positive number. Between 0 and 5, or rather that peak, we have negative slope, which means a negative dE dt term. So this is simply just the dE dt of plot 2. Now, the cool part is this, plot 4. Plot 4 is showing a dotted line, which is a PID control alone. That's what we saw here in plot 2. That's the proportional controller. But it's also showing what happens if we take that error rate, which we have in plot 3, and add it on top of plot 2. So plot 4 is a combination of 2 and 3. We're combining these two signals, superimposing them. This is linear control, so we can do that. When we do so, we notice that we have something that looks like so, the green line. Okay? That green line is the proportional plus derivative control. Now, what we notice here is that couple of things. Number one, the green line seems to have a larger amplitude than the blue line, so it's a little more aggressive in terms of the voltage being sent to the motor for correction of the ball position. And second, look at the peak. So with proportional control, you have a certain amount of voltage that is peaking at a later moment in time, whereas with PD control, that peak occurs sooner. And that is exactly why people want to use this, because that feature of having a predictive view of what's going to happen in the future but acting now is what makes the system more stable, because it's looking at the ball as it's moving and the rate of change. So if it's moving at a high rate of change, the voltage is going to act immediately, like now, instead of 5 seconds in the future, right? And that response time is dependent on the value of the D gain, okay? And control theories tells you how. How do I capture this moving ball, that rate of change of the error, and use it in my signal? And what's the magical number? What is the D gain that I need for this to go back within, I don't know, half a second or maybe a quarter of a second? So the customer decides how fast the ball goes back. But the derivative control essentially captures the rate of change and acts upon that in an earlier moment in time, as opposed to the proportional controller, which would be later. Now, if we were to plot the ball response with this voltage, the green voltage, we would see that this bump, that overshoot, would be attenuated. So we would have less of an overshoot, and this bouncing back and forth, the time that it finalizes, that's called the settling time, would be much shorter. Okay, so essentially we are improving our transient response. We're making it faster and more damped. Ideally, what you want is, if I'm commanding the ball to be at 5 centimeters, now I want my ball to go whoosh, whoosh, immediate, from 0 to 1. But that's not possible because of inertia, because of friction, right? Because of losses. Instead, we have to settle for something that kind of looks like a step. It goes from 0 to 1, but the less it looks like a step, the more we need to tune this, the more we actually want it to look like a step. And that's what D control does. It reduces these oscillations that overshoot and makes it faster, so you are essentially bringing all these curves closer to a step looking function, so that Y would follow R. Okay, and that's why we use D control. Now, this is all great and it's amazing because it's robust and it works. However, as with anything in engineering, there are always the pros and the cons. Okay, one of the cons is that if you have no idea how to get this value, you can destabilize a system even if it was stable. Okay, you can screw it up big time. If you don't know how to filter well your sensor, keep in mind the closed loop feedback system takes the sensor signal and feeds it back to the actuator. So if you have a very noisy signal, the actuator is going to be noisy also, and this beam is going to be back and forth, very noisy, right? And that's pretty terrible because the noise is going to be amplified in the system, and that's a problem with D control. Not a lot of people know how to filter properly. Okay, if you do not know how to select the integral control, you can also destabilize the system because of these so-called double poles. Okay, and those taking controls may bring memories back on what happens in this S plane. Okay, it's a plane that tells you the location of these poles, these time constants, and the closer you are to the imaginary axis, the closer you are to instability. So without dwelling too much in that theory, the integration destabilizes the system, while derivation stabilizes it. Okay, so in math, one is the opposite of the other. Okay, the antiderivative is the integral, and it makes sense that in the performance of the controller, they have this duality. Okay, one takes care of steady state, and the other one takes care of transient. One destabilizes, but the other one stabilizes. So it's not only the design process, but it's also a little bit of an art, if you think about this, because at some point in class we're going to talk about empirical tuning and how to get these numbers without necessarily doing the math. Okay, just by testing the system, throwing some signal in there and measuring the response, and just from that we should be able to get a transfer function. Very interesting topics. It's called system identification, and there's a great variety of literature out there on different methods in which to get this. Okay, so we're going to be talking about tuning rules, which means how do I get KP, KI, and KD without doing all that math. Okay, so in the next video we're going to go into Simulink and start coding a PID controller for any transfer function that we want to see. Okay, thank you very much.